What we're going to do now is move into the Q&A portion. We actually got some very good questions from the audience. So we'll go down starting at the very top. So first question is for Kevin. Can you talk a bit? Whoops, I just jumped. Okay. Can you talk a bit about the operating temperature for HBM2 memory stack, the limitations, and how to deal with it?
Sure. So the HBM devices from SK hynix will support temperature range from 0 to 105. Our commercial temperature range for all DRAM, including the HBM, is from 0 to 85. 95 is considered an extended temperature range, but we do support it. At 105, there is some caveat in running the device at 105. There is a certain conditions that our customers have to meet. Because of this public forum, I can't really go into the details, but you can, if you have any questions on this, just email me. I provided my email address, and I'll follow up with you on that. Limitation-wise, again, we realize the HBM device is sitting right next to an oven, the ASIC, but it is some distance away from it. So, and most of our customers do have heat sinks or heat dissipation solutions. Overall, through the thermal simulations that we've done internally and with our customers, the temperature range that we support is well aligned with their expectation.
Okay, thank you. So next question I can handle, it's a logistics one. How can we get access to the webinar post-presentation? So a couple comments there. First, I'll remind everyone that at the conclusion of the webinar, you will be receiving a link that will allow you to download a white paper that will go into a large amount of detail about the things we've talked about here on this session today. Beyond that, over the next day or so, we will be posting a replay of the webinar, and you will all get an email with the link to that. So feel free to listen to that again if there's some parts of it you want to re-listen to, or feel free to forward that to your colleagues inside your company so they can see it if they were not able to attend. Okay, so the next question is for Amkor. So the question, Paul, is what's the minimum pitch for interposer backside bump that you can achieve?
I think the best way to answer that is that the interposer interfaces with the substrate, and so typically what we're seeing is the range from the design side is anywhere from 150 to 180, and that's not necessarily a limit. That's more of a practical implementation, because if you go any lower, you're going to end up adding a lot more cost to the substrate, because it becomes an issue with the substrate suppliers being able to supply designs that were able to support sub 150 microns. So really, it's more of a practical limitation, and 150 would be probably the upper or the lower limit of where we're seeing designs. So anywhere from 150 to 180, and then up to 200.
Okay, thanks. So follow-up question also for you. What's the dimensions of interposers you can handle?
In this case, I'm assuming they want to know about the high side. So we have products that are larger than reticle size. So we're looking at interposer designs that are 40 by 28 millimeter range. So larger than reticle size.
Okay, thank you. Okay, the next question would be for Kevin. How many TSVs in an HBM or an HBM2 stack?
For this, again, this is part of our architecture and IP. We can't really disclose it. But if you look at the JEDEC spec, each channel has 212 signal bumps, if you will. So you could associate it with one TSV per signal, per channel. But overall, the HBM device has about a few thousand TSVs in it. Again, I can provide more details under NDA, and so please contact me. I'll provide you all those details.
Okay. All right, the next one's probably one that you could address as well. Would you explain a little bit more about the bump repair technology?
Sure. On the micro bump repair technology, the HBM defined by JEDEC several ways to repair a different type of bump, whether it's a DQ bumps or a control or command and address bump. But overall, you can use the IEEE 1500 protocol running either the X-test or LFSR or miser to identify and then subsequently repair the bump. The bump repair sequence is really a long sequence, so this is not a venue to talk about it, but there are redundant bumps, either DBI for the DQ or redundant command and address bump for you to replace the faulty bumps with.
Okay. So the next question, I think, is for Bill at eSilicon. Which commercial tool do you use for interposer design, or do you have an in-house tool?
So for interposer design, we're using a combination of off-the-shelf EDA tools as well as some eSilicon developed tools. The available package design tools that are in the industry are still appropriate for HBM-based interposer design. And the augmentation really has to happen because if you're using just a packaging tool, you still need to manage the signal to interposer to HBM correlation, and we're doing that through some tools that we've developed ourselves.
Okay, thank you. So the next question is directed at Paul at Amkor, but I'm not sure this is really what's being asked. The question is, when will process for 14 nanometer logic be available? And I think what you're asking there is, when will there be 14 nanometer ASICs installed on an HBM design? So I think Bill, again, from eSilicon is probably best to comment on that.
Yeah, so the short answer is we're doing it right now. We have 14 nanometer customer design in progress that ASIC sits on top of interposer next to HBM. So as far as availability of doing 14 nanometer ASICs on interposer, the door is wide open. We can do it today.
Okay. Now this next one, I think there might be a few folks that have a comment. I know, Bill, you have, maybe you can start. How do you control the warpage on large organic interposers? Isn't it difficult?
So the question is absolutely correct. One of the challenges here with dealing with interposer is dealing with warpage. There are a number of different techniques that we use to solve this problem. We have material today that is passing level 1 and level 2 qualification, which tells you that we have a solution. The specifics of what we're doing, we're declining to comment on in a public forum because we consider it part of our secret sauce and how we're putting together our ASICs today.
Okay, thank you. So next question is for Paul at Amkor. Where is the interposer foundry?
There are a number of interposer foundries that are supplying into the supply chain right now, and then of course we're actively working with new suppliers as they come online in order to bring more supply into the market.
Okay, thank you. So the next one is a question that I would say is primarily for Kevin at SK hynix. Is there a limit on the number of layers in HBM? And is heat dissipation an issue? Then he goes on to ask, is hybrid memory cube, HMC, an alternative promising design? And how do you compare it to HBM?
Sure. For this three-question series, the number of layers limit on the HBM. Of course, with any DRAM technology, there is an upper limit on the number of layers. Right now, within the DRAM industry, as well as the memory industry, the maximum number of layers you can stack is about 16 for NAND flash. For DRAM, which is an HBM technology, it's about 12. Beyond that, the TSV and signal redistribution just get really difficult. On the HBM device itself, SK hynix, we have up to 8 stacks of HBM core die. Heat dissipation isn't an issue, more so with the HMC technology because it sits, the DRAM core die sits right on top of an ASIC, if you will. Less of an issue with heat dissipation for HBM. In most of our customers' implementations, we haven't seen thermal dissipation as an issue yet. We do have customers that, as you know, from the graphics world that is in production right now, heat has not been an issue with that. How do we compare HBM within HMC. Both of them provide high bandwidth. HMC, because of the SerDes, provides bandwidth at more latency, and I would assume higher power than an HBM device. And overall, HBM implementation is very different from HMC. HMC is an external type of memory device. You just slap it on your PCB board and you're done. HBM-wise, you require a very, I would say more developed, established supply chain. And that's why we work with all of our partners like eSilicon, Amkor, Northwest Logic, and Avery, for example, to ensure that we have an established supply chain. So overall, I think there are advantages to using an HBM. There are also advantages to using an HMC. You just choose one that really fits your design.
Okay, thank you. So the next question is one for eSilicon. How is the reliability of the interposer overall?
So today, we have interposers which are qualified. They pass life tests, they pass storage tests, they pass humidity tests. Bottom line is we have in place qualified solutions that are reliable, will last an expected lifetime. When we look at what we're doing for customer programs, what we want to do is leverage the test chips that we've already put in place. So we want to be able to say, we've already done qualification of a device very similar to what our customers are doing, and we can have confidence that when we go to qualify our customer design, they're going to pass. However, with this technology, it's fairly easy to imagine a combination of ASIC size, ASIC process technology, interposer source, and number of HBM placements that has not been qualified. And that actually does drive us to do very specific test chips for customer engagements to prove out before we are doing that customer's ASIC that the configuration that we're going to build has a high likelihood of being a reliable product at the end of the day.
Okay, thank you. So we're on the home stretch here. In the interest of time, we can cover two more questions, and then we'll conclude the session. So the next one is a question that I think comes up a lot. Cost-performance comparison with traditional PCB plus DRAM approaches for things like a GPU application.
Okay, so when you're comparing HBM to a traditional DRAM, the first thing that you have to realize is you're comparing HBM with its terabit per second maximum bandwidth to, say, DDR. That means you need 40 DDR4 memories that are 16-bit wide running at 3.2 gigabit per I/O to have the equivalent bandwidth. Now, if you just look at the interface, the PHY interface of a DDR4, that's about 65 signals, which means in total you're looking at over 2,500 signals. Before you talk about power and ground, before you talk about any other signals that might be in your ASIC, that's simply not practical to put into any existing package today. So already we know that you're not comparing two solutions that you can actually do. But just for the sake of argument, let's ignore that and just keep going. So from a costing standpoint, what you would be comparing is the cost of 40 DDR4 memories, their board space, so you're going to need a bigger board to put those things down on, the cost of actually putting them on the board and yielding it. You're going to need a many-layer board, probably something in the 20-layer range, just to be able to route out to them. And then you need to look at your ASIC, where you need to save space for the PHYs that talk to all those DDR memories, and that's well over 200 square millimeter of expensive ASIC real estate. Now, compare that to HBM, where you'd be dealing with one memory, no additional board space, minimal board layers because you don't have to route out to the memory. The area on the ASIC that you need to reserve for the PHY is only 12 square millimeter, so it's something like 20 times better. And finally, you do need to add in the cost of the interposer in the HBM-based solution. But when you compare the two of them, what you're going to find is it's no contest. HBM wins. And really the right metric to be talking about in this scenario is not dollars per bit, but rather dollars per bandwidth. You're choosing HBM today because you need bandwidth and it's the way that you're going to get it. And when you look at the economics behind how you get to that bandwidth, you can see pretty clearly it's a winner.
Okay, thank you. So, final question, one with a little bit of a forward-looking character. Is anyone here looking into 3D integration of a processor core on HBM?
Yeah, we do. SK hynix, we're working with some of our strategic partners in looking into a 3D integration of the HBM. The limitation for this type of application would be the thermal dissipation from the processor or the ASIC onto the HBM device itself. So the processor has to be very low power in the single-digit wattage consumption. But yeah, we do have active program where customers are looking into this using ARM cores, targeting mobile space, or even in high-performance computing applications.
Okay, thank you. Okay, so with that, we will conclude the Q&A portion. I want to thank our attendees for the great questions, and I want to thank our presenters for the very informative information they shared.